Hey everyone, I'm asmollizard, and today you get to delve into my mind as you try to solve this energetics question where you want to find the experimental lattice energy of silver chloride. So do give it a shot if you haven't, and I'll see you in about 3 seconds. Alright, so this is how I would do it. Now, usually a Born-Haber cycle would work here, and usually there's a method that many people recommend, where you start off with the energy, this sort of axis, you have energy, and you start with 0. And this 0 would basically be the standard state, right? So Ag solid and chlorine gas, because you have one atom of chlorine, or so you only want half of the chlorine gas here. So that is usually the method, and then you incorporate the information from here. All right, it's possible. No one's stopping you from doing this method, but because it didn't specify for us to use that method, instead I'll use the other method of, well, energy cycle. And I'll start with the equation of the lattice energy of silver chloride. So don't forget your state symbols. So one more solid ionic compound formed from its constituent gaseous ions. So this is what we want to find. Okay, now how do we proceed from here? Well, use your pieces of information. The first equation, we have silver chloride solid. We over here have silver chloride solid as well. So we use that, incorporate that here. We basically have Ag plus aqueous plus Cl minus aqueous, and then this is simply minus 65.7 kilojoules. Then how do you proceed from here? Well, this is like logical thinking. We just use the enthalpy change of formation from silver ion, So solid silver, and well, chlorine standard state is chlorine gas, so you have 2 chlorines. Now we need to add a half because you only want 1 chloride ion. Okay, so this would be plus 106, this would be minus 167. All right, do not times the half. Don't forget your definition of enthalpy formation. One more compound formed from its constituent elements in their standard states. Right, so the emphasis is on the 1 mole of compound, not compound form, not from the reactant, not from the elements. Okay, then what's next? Enthalpy change of atomization of silver solid. Okay, so I'm going to draw the arrow downwards because we know we're going to close the loop already. So atomization, element to gaseous atom, 1 mole of gaseous atom form. Then, well, electron affinity of chlorine. So we get from chlorine atom, gaseous chlorine atom, to chloride ion in the gaseous state. So from here, and it's likely that it's going to come from here. Why is that so? Now, it's quite obvious, all right? Because the idea is when you have formation, basically you are using the elements in their standard states. And in the Born-Haber cycle, you'll be starting from here because the energy level for this is 0. So same thing from here. This chlorine atom would likely come from the standard state of chlorine, which is the chlorine 2 gas. So we add the first electron affinity, which is minus 349. All right, so we've used all pieces of information given, and we need to use the data from the data booklet. What are we missing? We're missing how do we form this silver ion, and it's likely going to come from the silver gaseous silver atom. How are we going to get this chlorine gaseous atom, gaseous chlorine atom? It will come from the chlorine gas. Right, so this is how you kind of piece your information together, and with experience you can easily know what these how to piece this information together. All right, so gaseous silver to gaseous silver ion, this is simply the first IE, and it is given as 731, and it's definitely positive 731 because it is an endothermic reaction, absorbing energy to take away 1 mole of electron. Then to go from half chlorine gas to chlorine atom, well, you're simply breaking the Cl-Cl bond. So because you're breaking bond, it is endothermic, absorbing energy. And because you're breaking only half mole, therefore half times the Be of Cl-Cl, half times 244 equals to 122. Solid to atomization, that would be plus 285. Okay, so we are done. All right, so now we just need to calculate everything. which simply, since you're going from here to here, you just need to go from downwards, this way, up way, and that way. Alright, so going downwards means we need to do minus of these two values, minus this value, then all these remaining values we just add them as they are. Alright, so we're minus 731 plus 349 minus 285. For the add the positive sign down here, we just add them. It's important to have the positive sign. Now we have minus 122 minus 285 minus. Okay, so now we just add the remaining as they are. So 167 minus 167 plus 106 minus 65.7. And this would give us, let me calculate them real quick. 106 minus 65.7. It is, oh, I think I typed something wrong. Did I? 285, 122. Oh, 16. Oh, I typed in 164. Wow. Minus 915.7. Which is approximately, well, again, convert everything to three different figures. Minus 916, because we're dealing with enthalpy change, a lattice energy is kilojoules per mole. Alright, so this is how you can solve these types of questions without the Born-Haber cycle. But if you're using the Born-Haber cycle, you start from the constituent elements, right, which is silver solid and chlorine gas. And because you only want one chloride ion, so half chlorine gas. Alright, but with enough experience, this method will be better, will be easier, as with more experience where you already know how this is going to go. Alright, you're going to involve ionization energy, you're going to be involving electron affinity, atomization, and bond energy as well. Alright, so this is how I solve this question with my lizard brain.